26209, grounding and bonding, section 5.0.0, separately derived systems. Explain how to ground and bond separately derived systems, explain how to ground separately derived systems, and state the requirements for grounding more than one building. A separately derived system is a wiring system whose power is derived from a source of electricity, electrical energy, or equipment other than a service. An electrical power supply other than that from a service with no direct connection to circuit conductors of another electrical source other than those established through grounding and bonding connections. Basically, the load side of a transformer is a separately derived system. If you have solar panels on your house, that's a separately derived system. If you have a generator, well, if you have a generator and the neutral does not tie into the main disconnect of the panel, the main panel of the house, it is a separately derived system. For whatever reason, they say if you use the same neutral running through the house as the neutral for your generator, it isn't considered a separately derived system. We'll see that. So here's a transformer supplied separately derived system. The secondary side of this is a separately derived system. There's no electrical connection with the service coming in and the secondary of this transformer. So the equipment grounding conductor, you have to ground the shell of this transformer to the main power coming in. And then this secondary side has to be grounded, just like the main bonding jumper at the service. This is called a system bonding jumper. It's for a separately derived system. It's a system bonding jumper. Separately derived system. The requirements of NEC section 250.30 pertaining to the grounding of separately derived AC systems are most often applied to 480Y 277 volt transformers that transform a 480 volt primary to a 208Y 120 volt secondary for lighting and appliance loads. The requirements provide for a low impedance path to ground so that line to ground faults on circuits supplied by the transformer will result in sufficient current flow to operate the overcurrent device. So it's just like a main bonding jumper, only it's for a system bonding jumper. Let me see if I can get to Article 100 definitions. Where is Article 100 definitions? Where are all of these? These are my in loving memory. Here's Chapter 1, Article 100 definitions. So if I go to bonding jumper, we'll see bonding jumper. There we go. Bonding jumper main. There you go. Bonding jumper equipment. Connection between two or more portions of the equipment. Grounding conductor. Make this a little bigger. Bonding jumper main. That's the one that connects the grounding electrode conductor with the grounded conductor, the neutral, and the equipment grounding conductors. The connection between the grounded circuit conductor and the equipment grounding conductor, or the supply side bonding jumper, or both at the service. So a system bonding jumper is the same. It's only on the load side of a transformer, but it serves the same purpose. It's the connection between the grounded circuit conductor and the supply side bonding jumper, or the equipment grounding conductor, or both, at a separately derived system. So you have this secondary of this transformer. It has to be bonded to building steel, just the same way the incoming service was bonded to the building steel. It has to go to building steel, it has to go to cold water, it has to go to an earth ground, either a plate, pipe, or rod ground. You have to ground this secondary, and it has to be grounded here at the neutral. This neutral, that'll be the system bonding jumper that bonds this neutral to the building steel. All right. NEC section 250.30 discusses the grounding of a separately derived system. Each voltage level that requires grounding must meet the requirements of NEC section 250.30A1. There must be a system bonding jumper that connects the equipment grounding conductors of the separately derived system to the grounded conductor. The grounding electrode conductor is connected to the grounded conductor at the same point where the system bonding jumper connects. The equipment grounding conductors are found in the feeder panel with the branch circuit supplied by this system. So It's like you just have a new, that's why they say it's separately derived. You have a new system that needs to be grounded and bonded, just the same as the incoming service. Grounding separately derived systems. So separately derived systems must be grounded as specified in NEC section 250.30. Examples of separately derived systems include, but are not limited to, transformers with no direct electrical connection between the primary and secondary windings, generator systems that supply power where the neutral is not connected to the utility system, such as for carnivals, rock crushers, cement batch plants, generator systems used for emergency required standby or optional standby power that have all conductors, including a neutral, isolated from the neutral or grounded conductor of another system, usually via a transfer switch. AC or DC systems derived from inverters or rectifiers. For separately derived systems that are required to be grounded, an equipment grounding conductor must be supplied with the primary circuit. This will provide a low impedance fault current path for the transformer case to the feeder overcurrent protective enclosure. So that's on the line side of that transformer. You have to have an equipment grounding conductor going back to the service on the line side in case something happens on the line side of that, on the primary side of the transformer. Along with the equipment grounding conductor, NEC section 250.30A1 requires a system bonding jumper to be installed for a derived system that must be grounded. The system bonding jumper may be placed in either the transformer enclosure or the panel, but not both. Installing it in both locations would create a parallel path with the grounded conductor, resulting in an unwanted current flow on the equipment grounding conductor. So you can either bond it at the transformer casing. There's the system bonding jumper on the secondary side. And here's the supply side bonding jumper going to the shell of the new panel. And here's the neutral conductor, but you wouldn't do both. Here they're taking it to the can, and instead of taking it to ground, they're taking it into the panel to the neutral bus. So here's the neutral, the midpoint coming to the neutral bar, and here's the supply side bonding jumper going to that same neutral bar, and then they have the system bonding jumper installed at the panel, and it's going to earth ground, grounding electrode conductor. So you either bond it here in the panel, or you bond it here in the transformer case, but not both. All right. Grounding electrode for separately derived systems must be the building or the structure grounding system. If the power source is located outside the served structure, it must be installed as directed in NEC section 250.30C. So a generator-based separately derived system is shown in figure 32. The way to determine that a generator serves a separately derived system is to examine the transfer switch. If the neutral and all the phase conductors are switched, then the system is a separately derived. If the neutral is not switched but solidly connected, then the system is not considered a separately derived system. So if it goes through the transfer switch to the load equipment, here's the feeder, here's the grounding conductor, and it's also going through the transfer switch. So this is a separately derived system, generator-based separately derived system. You're switching the neutral conductor as well as the feeder, the ungrounded conductors. For a separately derived system, the system bonding jumper can be installed at either the generator or any point in between. A grounding electrode conductor must be connected at the same point as the system bonding jumper. So again, you don't want to do both. You do one or the other, not both. Grounding at more than one building. So here we're taking a secondary panel off of the main panel. Here's the incoming feeder, the line going to the main breaker. Then we're taking a secondary, maybe 100 amp 2-pole breaker, and we're going out to a sub building. Here's the feeder. Here is the neutral conductor going to the neutral bar, and then the equipment grounding conductor goes with it and goes to a grounding bus bar in the separate building. But they have, look, system bonding jumper on the secondary, on this sub-panel, and they're also going to earth ground at this sub-panel. So it says the grounded circuit conductor and the equipment grounding conductor must both be extended to the second building. The grounded conductor is terminated on an insulated bus isolated from the metal cabinet, while the equipment grounding conductor from the main building is terminated on an equipment grounding bus directly connected to the cabinet. The equipment grounding conductor would be sized according to 250.122 based on the overcurrent device supplying the second structure. All grounding electrodes present at the second building would connect to the grounding bus. The grounding electrode conductor in the second structure is sized using Table 25066 based on the size of the feeder conductors. Table 2 shows the number and type of conductors that must be taken from the first structure to where the service is located in the second structure. So they're saying that this neutral bar is isolated from the back plane of the panel. It doesn't have an electrical connection to the back panel, the back plane. So here's the equipment grounding bus. The grounding bus is grounded to the box, and you take grounding electrode conductor to a grounding electrode to earth ground, and you take an equipment ground back to the main panel. But you don't secondarily bond this neutral, because that would create parallel paths. It would make this equipment grounding conductor now a current carrying conductor. It would act as a secondary neutral. So here's Table 2, the number of conductors between the structures. All right. If there are no grounding electrodes at the remote structure, a grounding electrode must be installed unless the structure is supplied by a single branch circuit that includes an equipment grounding conductor. Possible electrodes include underground metal pipe, metal in-ground support structure, or concrete encased electrodes. Rod pipe or plate electrodes may also be permitted in accordance with NEC section 250.52. Note that this method may only be used under the following conditions: when an equipment grounding conductor is not installed with supply to the second building, when there are no continuous metal paths bonded to the grounding system in both buildings, when ground fault protection has not been installed on the common electrical service in the first building. These additional provisions prevent the possibility of parallel current paths between the grounded and the grounding conductors, as well as nuisance tripping of a ground fault protective device. All right. Section 5 review. Which of the following is considered a separately derived system? And number 2 is when grounding at more than one building, the grounding electrode conductor at the second building is sized based on the size of the feeder conductors using. All right. Let's go on to section 6. Testing for effective grounds. Explain how to test for effective grounds. State how to measure earth resistance using the fall of potential method. Explain how to complete a 3-point test. An earth ground resistance tester may be used to make soil resistivity measurements or to measure the resistance between an installed grounding electrode system and the earth. The meter shown in figure 34B is designed to drop over the top of a grounding electrode for measurements. So ground resistance, the resistance of the earth to current flow, also can refer to the resistance between the grounding electrode and the surrounding earth. Warning: ground resistance testers can be hazardous to both equipment and personnel if improperly used. Always check with your supervisor before using a ground resistance tester. So here he's using a ground resistance tester, and he's putting it around this ground rod to see what the resistance per foot of earth is. He wants to know. These testers are often used for testing electrical systems after they're installed, but before normal voltage is applied. The test is made after all conductors, fuses or circuit breakers, panel boards, outlets, etc. are in place and connected. Satisfactory installation resistance values vary with soil conditions and the installation. Charts supplied with the instrument should be consulted for the proper value of a particular installation. So, connections to the earth can be made using one or more grounding electrodes. A ground grid is a system of grounding electrodes interconnected by bare cables buried in the earth to provide a lower resistance than a single grounding electrode. and a ground mat, system of bare conductors or on or below the surface of the earth connected to a ground or ground grid to provide protection from hazardous voltages. A good grounding system limits system-to-ground resistance to an acceptably low level. This protects personnel from hazardous high voltages during a fault in the equipment. In addition, equipment damage can be limited by using ground currents to operate protective devices. Ground testing is also used to verify the adequacy of a new grounding system, detect changes in an existing system, and determine the presence of hazardous step potential and touch potential. So step potential, let's say there's a short circuit and this Eiffel Tower becomes energized. It's going to radiate out in the earth. So you might have a 1,000 volts at one point and only 500 volts at another point. That's a difference of potential of 500 volts. And if it is 3 feet or less, you can step across that and you can get hurt. You can get killed. It's called step potential. And you have to, if a crane ever touches a high line, let's say there's a crane operator and that crane touches this high line, that crane operator can't jump out of that crane and run away. There's step potential and he'll probably get hurt or killed. If he can't wait for medical services, for emergency services to come out to turn off the high line, if he's panicking, he can jump out with his feet together and bunny hop out of the area, keeping his feet together and avoid that step potential, that step voltage. All right. I'm not going to read the case history. Assuming a power source resistance of 40 ohms and a short circuit between the power line with a voltage of 5,000 volts and a steel tower would produce 100 amps of short circuit current. Here's their figure. They used math. So they came up with 100 amps of short circuit current. A person touching the tower would be subjected to the voltage developed across the ground resistance. So that's 1,000 volts between the power and the ground. Statistics vary widely concerning what may be considered a dangerous voltage. This depends largely on the body resistance and other conditions. However, to limit the touch potential for this situation to 100 volts, certainly safer than 1,000 volts, the ground resistance for the tower would have to be less than 1 ohm. So they're going to try to teach us how to measure earth resistance. 6.1.0 Measuring earth resistance. Several methods are used for measuring the resistance to earth of a grounding electrode. One of the most common is the fall of potential method. In a nutshell, you have an instrument, and that instrument is going to put out voltage and current. So you have an auxiliary potential electrode, that's voltage, and you have an auxiliary current electrode. And you put them X amount of feet away from this ground rod, this grounding electrode that you want to test. Let's say you put this number 2 at 100 feet, you'd put this number 1 at 62 feet. You put it at 62% of the distance to the second one. And then you would start reading your potentials. You can move this one on the inside. You can move it along and get it closer to this auxiliary current electrode and further away from the grounding electrode. And it's going to create a graph. In this method, auxiliary electrodes 1 and 2 are placed at sufficient distances from the grounding electrode X. Then a current is passed through the earth between the grounding electrode X and the auxiliary current electrode 2 while being measured by an ammeter. The voltage drop between the grounding electrode X and the auxiliary potential electrode 1 is indicated on the voltmeter. It can therefore be calculated as follows. So the following problem may arise with the fall of potential method shown in figure 36. Natural currents in the soil causes the electrolytic action, can cause the voltmeter to read either high or low depending on polarity. Induced currents in the soil instrument or electrical leads can cause vibrations of the meter pointer. Resistance in the auxiliary electrode and electrical leads can introduce error into the voltmeter. For these reasons, many ground testers use a null balance metering system. Unlike the separate voltmeter and ammeter method, this instrument provides a readout directly into ohms, thus eliminating calculations. So basically, they're going to set this up, and it's hard for me to explain it, but here are your three probes, and here's a rheostat. It's a potentiometer with a calibrated dial, and it's coming from a multi-tap transformer. And basically, you're going to take readings. Let me see if I can find there. They show us there now. All right. Now on the next page, I think they show us a graph, and that graph is going to show us when it levels out, that's the earth resistance. So when switch S1 is closed, the battery energizes the coil of vibrator V. The vibrator reed V1 begins oscillating, thereby producing an alternating current in the primary and secondary windings of T1. The negative battery terminals connected alternately across first one and then the other half of the primary windings. So, all right, I'm not going to read all of this. Not trying to short you, not trying to confuse you, but I just want to get to the earth electrode resistance. I want to show you that graph. I'll come back to this page in a second, but here's what the graph looks like, and you can set it up differently that it'll give you a flatter graph. This one, what's happening is it's giving you a certain amount of current flow as you're moving, as you're increasing the potential, the voltage. And then at some point, this curve flattens out, and then it starts to again climb. And that's as you're moving this middle probe in the soil, and it gives you this kind of a graph. Well, this graph that levels off, that's the actual resistance of the earth, of the ground itself. It might be 7 ohms, it might be 10 ohms, but you can use that to calibrate the resistance of your ground rod. You'll have a ground rod, and you can use that information to calibrate it. You can say, well, I'm reading 17, but we have 12 ohms of earth resistance. So if I subtract 12 from that, I've only got 5 ohms to ground on my ground rod. And that's well below the 25 ohms that you need to supplement if you have 25 ohms or more. So we've only got 5 ohms. Basically, that's what they're doing. That's how it works. You've got these three probes. Well, this one is the actual grounding electrode, and then these two are a potential electrode and a current electrode, and you move it along as you take the readings, and it gives you this graph. All right. All right. I'll be right back. Wait a minute. Let me go back to that other page. There we go. So earth electrode resistance. Now that we've seen that graph, now I think I can explain this a little bit better. Current in a grounding system is primarily determined by the voltage and impedance of the electrical equipment. However, the resistance of the grounding system is very important in determining the voltage rise between the ground electrode and the earth, as well as the voltage gradients that will occur in the vicinity where the current is present. So 3 components contribute to the resistance of grounding system: the resistance of the conductor connecting to the ground electrode, the contact resistance between the ground electrode and the soil, and the resistance of the body of the earth immediately surrounding the electrode. Resistance of the connecting conductor can be dealt with separately since it's a function of the conductor cross-sectional area and length. Current from a grounding electrode flows in all directions via the surrounding earth. It's as though the current flows through a series of concentric spherical shells of equal thickness. Contact resistance is usually insignificant if the electrode is free from paint or grease. It goes on to say the shell immediately surrounding the electrode has the smallest cross-sectional area, therefore its resistance is the highest. As the distance from the electrode is increased, the shell becomes correspondingly larger while the resistance falls. Finally, a distance from the electrode is reached where the additional shells do not significantly add to the total resistance. From a theoretical viewpoint, total resistance is included only when the distance is infinite. For practical purposes, only the volume that contributes most of the resistance needs to be considered. This is known as the effective resistance area. It depends on the electrode diameter of the driven earth. 3-point test, that's the one that they're going to ask you about. To measure the resistance of a grounding electrode with most ground testers, an auxiliary current electrode and an auxiliary potential electrode are required. The current electrode is placed at a substantial or a suitable distance from the grounding electrode under test, and the potential electrode is then placed at 62%. So if you put the current electrode at 50 feet, then you're going to put the potential electrode at 31 feet. It's going to be 62% of that distance. If the current electrode is too near the grounding electrode, their effective resistance areas will overlap, as shown in figure 38. If a series of measurements are made with the potential electrode driven at various distances in a straight line between the current electrode and the grounding electrode, the readings will yield a curve as shown in figure 38. So these two were too close together, and you got this curve. So as you adjust the distance and make sure that they're far enough apart, then you get this flat spot that tells you what the actual resistance of the earth is. No definite distance from the current electrode can be forecast, since the optimum distance is based on the homogeneity of the earth, depending on the grounding electrode, the electrode diameter, etc. However, for a starting point of a single driven grounding electrode, the effective radius of the equivalent hemisphere can be computed. The curve of figure 40 can be used for initial placement of the auxiliary electrode. So, all right. Using the practical method of moving the auxiliary potential electrode 10 feet to either side, the 62% a curve can be plotted to determine if the current electrode spacing is adequate, as depicted by the curve flattening out between points B and C. All right. So there you go. Once you get a flat spot in your curve, then you know that you have a good distance on your current probe, and 62% of that to the potential probe. If the voltage drop between a grounding electrode and an auxiliary potential electrode is 10 volts, and a current of 10 amps is passed between an auxiliary current electrode and the grounding electrode, then the resistance is what? Well, R equals E divided by I, right? When completing a 3-point test, the potential electrode is placed at what percentage? All right. This concludes 26209 grounding and bonding. I hope it wasn't too boring for you. It's a dry subject. It's just something that you're really not going to understand until the first time you actually do it in the wild. If you got anything out of the video, please give me a thumbs up and consider subscribing to my channel. And I really do appreciate it. And I'll see you on the next video. I gotta go feed my dog. Bye. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.